So, what in the world does a spinning hexagon have in common with a high school algebra formula or the arc of a ball flying through the air? It sounds like the start of a really weird riddle, right? But the answer is actually one of the deepest ideas in all of science: symmetry. Today, we're going to pull back the curtain on this secret language that really truly governs our universe.
Okay, let's really think about this for a second. On the surface, what could these three things possibly share? One's about geometry, nice and visual. One is pure algebra, for finding x. And the last one is straight up physics, the laws of motion. They really seem like they belong in completely different worlds.
And yet, they are all connected by the exact same powerful idea. There's this golden thread that runs through all of them, tying together math and the very fabric of reality. So, what is it? What's the big secret? Well, that's the puzzle we're going to put together right now.
Let's start with the kind of symmetry we all get, intuitively. We see it everywhere, right? In the reflection of a butterfly's wings, the petals on a flower, the balance of a human face. It's that feeling, a sense of harmony that just looks right to us. But in mathematics, symmetry isn't just about looking nice. It's something you do. It is an action, a transformation. Think about a perfectly symmetrical face. If you could flip it horizontally, like in a mirror, it would look exactly the same. Or take a hexagon. You can rotate it by 60 degrees, and bam, it lands perfectly back on itself. That action, that flip or that turn, that's the symmetry.
But of course, mathematicians weren't just happy with the gut feeling. They wanted to go deeper. They wanted to create a formal language, a kind of universal grammar, to describe every single possible symmetry of any object you could ever imagine.
And that whole language is built around this one powerful concept called a group. Now, a group isn't the object itself. It's the collection of all its symmetry actions. For that hexagon, the group is the set of all the different rotations that leave it looking unchanged. And these actions, they have to play by a very specific set of rules. And it really comes down to these three simple rules. First, there always has to be an identity action, which is just the fancy term for doing nothing at all. Just leave it alone. Second, if you do one symmetry action and then you do another one right after, the combined result has to also be a valid symmetry. That's called composition. And finally, every action has an undo button, an inverse. So a 60-degree clockwise turn is undone by a 60-degree counterclockwise turn. That's it. You have those three things, you've got yourself a group.
Okay, so symmetry for shapes, that makes sense. We can see it. But hang on, because this is where our story takes a truly wild turn, all thanks to a young, brilliant French mathematician named Évariste Galois. He started asking a question nobody else was even thinking about.
He was wondering, how can something totally abstract, like a polynomial equation, have symmetry? I mean, you can't rotate an equation, you can't flip it over. What is there to even transform?
Galois' incredible insight was that every single polynomial has a hidden symmetry group. The trick, he realized, wasn't to look at the equation itself, but to look at its solutions, the numbers we call its roots. That's where the symmetry was hiding all along. Let me show you what I mean with a super simple example. Let's take the equation t squared plus 1 equals 0. Its answers, its roots, are the imaginary numbers I and negative I. Now, here is the big idea. What if you just swapped them? Everywhere you see an I, you replace it with negative I and vice versa. It turns out all the fundamental truths of math stay exactly the same. The roots are, in a way, indistinguishable. That action, that swap, is a symmetry.
This collection of all the valid ways you can swap the roots, well, it forms a group. It follows those same three rules: identity, composition, and inverse, just like we saw with the hexagon. And this is what's called the polynomials Galois group. It's the unique fingerprint of an equation's hidden symmetry.
And this visual just makes the connection so clear. Take a look at the roots of this fifth-degree polynomial. When you plot them on the complex plane, they form a perfect pentagon. It's amazing. It's like the corners of a shape. You can swap and rearrange these roots, but only according to the strict rules of their Galois group. The abstract symmetry of algebra suddenly has a face.
So why does any of this matter? Well, here's the incredible payoff. Galois proved that you can only solve an equation with a nice, tidy formula if its symmetry group is, quote, solvable, which is just a way of saying it can be broken down into simpler parts. And it turns out, for equations of the fifth degree and higher, their Galois groups are often way too complex, too tangled up. And that is why there's no general formula for them. Not because we haven't found it yet, but because their symmetry proves it's literally impossible.
So, symmetry governs shapes, and it even decides which equations we can solve. But the story that's even bigger. Now we're going to leap out of the abstract world of math and into the concrete reality of physics, all thanks to the work of another incredible genius.
You know, this quote from a Reddit user just nails the feeling of this next connection. It's one of those ideas that once you see it, it just changes how you look at everything. It connects symmetry directly to the most fundamental laws of our universe. The mind behind this whole revolution was Emmy Noether. She was working in the early 1900s, and she developed a theorem that Albert Einstein himself called one of the most beautiful concepts in all of mathematics. And here it is, her incredible insight, known as Noether's theorem. Simply put, it says that for any continuous symmetry you find in the laws of nature, like a law that doesn't change as you move through time or space, there absolutely must be a corresponding physical quantity that's conserved, meaning it can't be created or destroyed. And this is where it gets so real. The laws of physics work the same today as they did yesterday, right? That's a symmetry across time. Noether's theorem proves that this demands the conservation of energy. An experiment will give you the same result here as it would on the other side of town. That's symmetry in space, and it requires the conservation of momentum. Remember the thrown ball from the beginning? It follows a predictable path because of this principle. Symmetry isn't just a pretty idea. It's the reason we have these conservation laws that make our universe stable and predictable. So let's pull that golden thread all the way through and tie this all together. We started this whole thing with 3 ideas that seem to have nothing to do with each other. We began with the simple visual symmetry of shapes, the flips and turns we can all see and understand. Then we took that wild leap into abstract algebra, and we discovered that even equations have these deep, hidden symmetries in how their solutions relate to each other. And finally, we saw how that very same principle governs the entire universe, where the symmetries of physical laws are what create the fundamental rules that make reality work. From a hexagon to the quadratic formula to a thrown ball, they're all just different expressions of symmetry. It is a fundamental language that describes our world on every single level. Which really leaves you with one last big question. If this single language has already helped us unlock so many of the universe's secrets, what else is out there just waiting for us to understand?